Welcome to part 2 of lecture 14. And we're going to continue on with looking at how we might optimize a location for some station within a facility, or how we might optimize location of facilities. So in this case, we're going to be dealing with a company called La Rosa, and let me adjust this just a little bit there. And yeah, okay, so, and I'll increase the size of this there. Okay. So, the case of the La Rosa machine shop, LMS, La Rosa is studying where to locate its tool bin facility on the shop floor. They want to be fair to the workers in each of the production stations. Management has decided to try to find the position of the tool bin that would minimize the sum of the distances from the tool bin to the 5 existing production stations. So we're going to have 2 decision variables. X is going to be the horizontal location of the tool bin on our Cartesian coordinate, and Y is going to be the vertical location of the tool bin. And then we have the locations of the 5 other production stations in the problem as well. So here we have a chart of the other 5 stations: the paint, the fabrication, the subassembly, the assembly, and there's 2 subassemblies, subassembly 1 and subassembly 2. And then the question is, where do we put our tool bin? So we have existing we have existing locations in terms of coordinates for each one of the 5 workstations. The tool bin is here at the bottom of that list, and then the distance is here, and of course it is a square root function. So we want to minimize the sum of these square roots, and of course we're squaring the differences between them like we would in the calculation of a distance. And so this is a nonlinear function. The coordinates for the tool bin, I just put in a 1 and a 1. If I change, let's say, make this a 2, and then you can see all the distances change. And we want to get this sum of the distances minimized between all of the workstations and the subassembly and the tool bin. Okay. So, of course, we measure the distance from a station to the tool bin with the Euclidean straight line distance function, where we take the coordinates of 1, we subtract the x coordinates of both the points, add the difference, and we square those, and then we add the difference of the y coordinates squared, and then we take the square root of that. And that's going to give us the distance between 2 points. And of course, here's our 5 areas that already exist. And then here's the what we want to do. This is a minimization problem. And these are x and y is where we're going to vary x and y to find out which xy pair gives us a minimum distance between all the stations. So the distance from the xy to each one of the workstations, we're going to take x and y and subtract the xy coordinates of each workstation in turn from them, take the square root of those and add them up. And we get those xy values here. Fabrication is at x1, y4. And then we have, 1 and 4 in here. And then we can get a solution to the problem by using our optimization function on the objective function. So we'll go ahead and run that, and it shows that we don't necessarily have to have your normal constraints in a problem. So again, let's take a look before we go there. Here's our objective function. We want it's the sum of these three cells, and we want to minimize that. Here, each one of those cells is that calculation we saw on the slide between the coordinates we have currently for toolbin and the fixed coordinates for each one of the workstations. So let's take a look at how we resolve this. Again, it's going to be nonlinear. We don't have any constraints. We just have the optimization function itself. We want to, with nonlinear functions, they can be optimized oftentimes on their own. And so that's what we'll attempt to do here. Going to minimize this distance problem by changing variables B18 and C18. In other words, the X and Y coordinates of our tool bin. So let's go ahead and run this. And it did find a solution, and our tool bin moved from 1, 1 up to here, and that's 0.2.23 X and 3.35 basically for Y. Okay, now let's look at forecasting the adoption of a new product. Okay, let's take a look at forecasting the adoption of a new product. And there's a model called the Bass forecasting model, and in the book they used an independent film studio versus a film versus a blockbuster to show how you could forecast potential sales or potential customers for this type of product. Obviously, the Hollywood studios are going to be most interested in a product like this because they're always coming out with new products, new movies. And so if they can get a good sense of what their demand would be, then that would really help them immensely. So what we are looking at is we want to minimize the error in the particular forecast that we're making. So that's what we're going to minimize here. And we've got the Bass equation uses, or the Bass formula uses these parameters. So let's take a look at those parameters. Again, this is developed by a guy named Frank Bass. It's a nonlinear optimization that's used to estimate the parameters in his forecasting model. The model has 3 parameters that have to be estimated, and they are going to be, and the number of people who eventually adopt the new product. Q, that is the coefficient of imitation. And P, the coefficient of innovation rather than imitation. And for any time period, he has some variables that denote the number of people who have adopted the product accumulatively through that period T1. And then M, which is the number of people estimated to eventually adopt, is the number of potential adopters remaining at time T1. So the likelihood of adoption due to imitation is going to be given by this formula, Q, and again, Q is the coefficient of imitation, and P the coefficient of innovation. And then the likelihood of adoption is P plus Q times this cumulative customers at any time divided by M. And here we see a graph of the box office revenues for an independent studio. And it's two different films, an independent studio film and a summer blockbuster, as we can see over the first 12 weeks after release. Box office revenues for time period are not the same as the number of adopters, strictly speaking, but they're a good proxy for it. And the authors conclude that it's appropriate to use the Bass model in this particular case. So here's what we get for our nonlinear optimization is we want to minimize the sum of error squared subject to we've got the various functions and that's going to be what we're going to be minimizing subject to these particular. So the constraints are F, the forecast of the number of new adopters during that time period, and then of course CT is the actual number of people through the period CT. And then the error is going to be the difference between the two. And we want to minimize the sum of all the errors. And here we see the revenues and the cumulative revenues. And then our nonlinear Bass model for accomplishing all this. So our parameters are going to be, again, P, the coefficient of imitation, Q, the coefficient of innovation, and M, the number of potentially new customers that we have. And we have our highest revenues for the blockbuster, I'm not the blockbuster, the independent movie in week 4. Whereas the blockbuster starts out high and then gradually drops off. So there's an innovation and imitation effect for the independent studio film. It starts gradually increasing over time, and then it reaches the point where it begins that same type of semi-exponential drop in sales like the blockbuster after it reaches a point where it's saturated and people know about it. So when we plot the forecast values from the Bass model with the observed values, we see that there is, it has a similar shape, although it's not as angular, and it's a little off in terms of the predicted forecast in terms of millions against the actual, but it might be enough to give us a good indication of what our long-term success might be, and whether or not we want to pour more advertising into this or some other management decisions. So in summary, the BAS model does a good job of tracking the revenues and is forecasting under the assumption that sales of a new product will behave in the way that is similar to a previous product for which these coefficients of imitation and coefficients of innovation have been calculated, and then to subjectively estimate M, the potential market for the new product. And so we saw an example of this in our spreadsheet right here, and we have the forecast values versus the cumulative weekly sales, and we're going to minimize our some of the squared errors by changing C18 through C20, the parameters of the BAS model. We're going to use the GRG, and we cannot have a negative number of customers, and we can't go over 500 million customers. That might be a limit to this type of movie, for example. So that's how we would set up something like this, a very complex product forecasting model that's nonlinear. Okay, so that concludes our discussion of nonlinear models. And essentially what we're looking at is there's nonlinear terms in either our constraints or our objective function. And we noted that most of the models that we'll be looking at in the business world probably will end up being nonlinear because you have this relationship between price and quantity. So when you have something like that, that means that when you multiply price times quantity, but quantity is a function of price, you're going to get nonlinear terms. So many times we'll be looking at that. We can also look at it, and we used Solver to solve one of those kind of problems with the par golf bags. We also looked at perhaps we don't even want to add constraints in, like the number of hours available for the tasks in the golf bag problem. But we just want to do, we have a function where we're trying to minimize distance between existing locations. And we looked at that with La Rosa, and we minimized the distance between a newly to-be positioned tool station and the 5 existing workstations. We didn't need to add constraints there. This was a pure minimization problem. It wasn't an optimization with constraints, it was an optimization plane. And Solver can do those. So we did that, and it worked fine. And then finally, we looked at an exotic and rather complex model developed by Frank Bass for predicting future customers for a product. And it used what he calls his coefficient of imitation and his coefficient of innovation to come up with a model for predicting the number of customers, and then coming up with a number of customers in the prediction that minimizes error would give us some kind of estimate. And when we tracked the actual versus the forecast, it wasn't far off. I mean, it wasn't an exact match, obviously, but it wasn't far off. So that was just the Frank Bass model was more, I think, to show you potentially where things that are fairly complex and exotic, you can still apply nonlinear functions in Excel to help come up with some data-driven decisions. All right, thank you.